All right, so welcome to Absolute Age Dating. This is the class lecture on that. So last time we learned about relative age dating, understanding which rocks are older, which rocks are younger. This is how geologists figure out exactly how old rocks are. So you can see we have the relative age over here, like stacked up, Paleozoics older, Mesozoic, Cenozoics younger. And we can actually use some technology to absolutely date those rocks from those time periods. Gives us the actual start dates for the finish dates for those time divisions. All right, and here's a kind of another look at this, more specific, where we start way back in the pre-Archean. That is the beginning of Earth history, 4.5 billion years ago, roughly, into the Archean, Proterozoic, and then the Phanerozoic up here. So how do we do it? What do we do to actually date rocks or even living things from the past? Well, we first have to have an understanding of isotopes. And so if you're familiar with the periodic table of elements, each element has isotopes of itself. And so this is oxygen is the element, an atom of oxygen has a certain number of protons, that's its atomic number, but it can have varying numbers of neutrons in its nucleus. Okay, so that is what an isotope is. An isotope is something that has an element that has the same number of protons, because that gives it its properties. That's its placement on the periodic table. But the number of neutrons, neutrally charged particles, can vary. Isotopes are those elements or those ions, those isotopes that have different numbers of the neutrons in their nucleus. Okay, so you can have an O16 one, which is 8 protons plus 8 neutrons in the nucleus, or you can have the O18 isotope, which is 8 protons plus 10 neutrons, and so on and so forth. And different elements have different isotopes that are stable and that exist in nature. All right, so what happens with different isotopes? Some are unstable. And so what you have is you have a nucleus in a parent atom, like that O16 or O18, and over time they decay. And what happens is that parent nucleus decays away into 2 different particles. So in this case, alpha decay, you get a daughter nucleus, which is going to be a different element in a lot of cases. It's going to have a different number of protons in its nucleus, and an alpha particle, okay? So that's alpha decay. Here we go. Here's another example of specifically how that looks. So here is the uranium-238 isotope, okay? There's also like uranium-235. Those are the 2 most common ones. And we have a new nucleus, so we get a new element, actually, thorium. Over here, we go from uranium. The decay produces a daughter, what we call a daughter isotope, thorium-234, and also an alpha particle, which is, of course, that helium particle. Neutrons are in blue and protons in red here. And this is happening with lots of different elements. So how does that going to help us? Well, here's another possibility. Carbon-14 is actually a beta decay, where it goes from a carbon-14 to a isotope to a nitrogen-14 plus an electron plus an anti-neutrino. And so these 2, in beta decay, we can go from carbon to nitrogen. All right, so how long does it take for those parents to decay into daughters? Because if we can measure the ratio of the parents to the daughters, and we know how much parent we started with, we can figure out how much time has passed. All right, well, we do that by using a concept called the half-life. So if you have 40 milligrams of something like uranium, and after 1 half-life, half of that has decayed into daughters. After 2 half-lives, half again has decayed into daughters. So this is how radioactive half-lives work. All right, so for example, we start with a rock and has uranium in it. Lots of igneous rocks have uranium in them. We can then, if you look at the daughter sometime later, you will also have the daughter, like the lead. So from uranium turns into lead as the daughter. And then we might have all uranium to start, and then now we have about half and half. So one half-life has passed. Now, it looks simple here. It's actually super complicated. And there's the picture of what actually happens. So this is the full uranium-238 decay series. It doesn't just go from uranium-238 to lead-206. It actually goes through a whole bunch of different isotopes of different elements to get there. And notice this half-life of this uranium. Holy cow. 4.5 times 10 to the 9th years. I mean, that is a long, long, long half-life until we get down to lead-206. All right, but in the middle there, we have some that have like really little short half-lives, like 3.8 days or 3.3 minutes for polonium-218. But anyway, I just wanted you to see that it looks simple when we show this picture. It's actually pretty complicated how this works. All right, and here we love this picture, which is the radioactive decay data. We have these isotopes, carbon-14, potassium-40, uranium-238, and rubidium-87. These are all the systems that geologists and archaeologists tend to use to date the items they're trying to get an actual age for. And here's the disintegration, what happens. We go from carbon-14 to nitrogen-14. In the potassium, when we go from potassium-40 and we create argon and calcium on billion-year timescales, and then we go U-238, that's a common one, to lead-206, 4.5 billion-year timescales, and rubidium, strontium, ooh, that one's even longer, for, in the billions of year timescales for the half-life. All right, so really different, because look at carbon. Carbon is only a 5,000-year half-life, so it's much shorter, and it's also different. Carbon, we don't have a lot of carbon in rocks, right? Carbon is what living things are made out of. So let's keep exploring this concept. So here's a question for you. When we think about dating rocks or archaeological things like formerly living things, what event or what thing are we actually dating when we radiometrically date a rock using the parent-daughter ratio and the half-life? Well, for living things, we're actually dating the death of that living thing. There is carbon exchange with the atmosphere in living things, but upon death, that stops, and that starts the clock that we use to date that item. All right, so for igneous rocks, very good. You can use radiometric dating for igneous rocks pretty easily. What are we dating? We're actually dating the date of crystallization. When did crystallization when did those minerals lock into place? And they aren't magma anymore, now they're solid crystals. Metamorphic rocks. If we try to use radiometric dating to date metamorphic rocks, what are we dating? Well, we can't go back to the parent rock. We can't. The metamorphism erases and kind of resets the clock on radiometric dating. We're actually dating the date of metamorphism, which, how useful is that? Maybe not so useful. That could happen over time. It's kind of complicated, and so we really are not able to use radiometric dating very effectively for metamorphic rocks. Sedimentary rocks. What are we dating? What event are we dating? Remember, sedimentary rocks are often created from the shells of other animals, the pieces from other rocks. Who knows what we're dating if we try to date a sedimentary rock? So you really are not able to get the actual age date of a sedimentary rock at all, because they're too complicated. They're made up of pieces of other rocks, and it's just too hard. All right, so next question. Can we use the carbon-14 system to date igneous rocks? Why or why not? And the answer, of course, is no. There's no carbon in igneous rocks. Any magma, any melting would completely obliterate any carbon. So we cannot use carbon with its 5,000 approximately year half-life. We cannot use that to date any igneous rocks. We're really stuck with these other systems, potassium-40, uranium-238, and rubidium-87, with their billion-year half-lives. So we have to work around that. But carbon is great at dating living things, which is great because living things are more recent and we want to know more recent dates. So that half-life fits that. All right, can we use the other systems to date young igneous rocks? Really hard to do. As you'll see from your assignment today, and we figure out like how does the half-life relate to how long we can, how old a rock can be that we can use to date it. It's really super hard to do with these long half-lives, but anything that's, millions of years old, we can absolutely date using these systems. Younger ones that are in the thousands is really tricky, but there is a way to do it. So how can we figure out the age of other rocks that can't be dated? Young igneous rocks or sedimentary rocks or metamorphic rocks? Well, one of the ways we can do it is we can look at, date what we can, date anything with carbon, date igneous rocks that are around it or intruding into it. We can easily get those. And then use our relative age dating techniques in concert with our absolute age dating techniques or our radiometric dating to try to lock down the dates of things. We can use the fossils, index fossils as well, and we can try to start to get parameters on how old rocks are that can't be directly dated. There's another way to get young igneous rocks that's been a vexing problem for a long time is how do you date those young basalts on the ocean floor? And there is a way to do that, which I can show you right here. And the way we start to do that, that's a brand new thing we've been doing. I did a little bit of this in my PhD work where we actually don't use the U38 parent to daughter ratio to lead. We actually go in and maybe look at a uranium thorium parent daughter here, or a radon polonium, or a lead bismuth, or something like that, where we have shorter half-lives, and we can look at ratios in the middle of this long string of decays, and we can start to get shorter half-lives that give us a chance to figure out younger rocks and how to date them. All right, so your assignment today will show you how radiometric dating and decay works, and you'll see it. You're going to kind of simulate it using pennies, and it's going to give you a much clearer view of how this all works to actually date rocks. Thank you.